Hagia Sophia was finished 1500 years ago, and we still don't fully understand how it works. Modern science can't explain all of it. The engineering, it still challenges architects today. The world's leading architects, this ancient dome, it defies gravity. There are 10 hidden principles behind that. 10 principles that are reshaping modern design now. Builders back then, they had no computers, yet the structure survives massive earthquakes. It's still standing. There's a mortar they used, a secret in that mortar. It's held for over 1,500 years. This ancient masterpiece, it reveals something about our own potential to build things that last for the ages. Constantinople had just been through the Nika riots, a week of violence. The city center was burned, and the old church there was completely destroyed. So the Emperor Justinian, he looked at that ruin and he saw something else. He saw a chance. He didn't want to just replace the building. He wanted to make a statement. A statement about God's power and his own. He wanted a dome, but not a normal dome. He imagined a dome so huge and so light it would look like it was just hanging from the sky. Like a piece of the sky brought down. That was the vision, but that kind of vision, you can't give it to regular builders. So Justinian went to two scholars, Isidore of Miletus and Anthemius of Tralles. One was a geometer, the other worked in physics, mechanics. They weren't builders in the usual way, they were theorists, mathematicians, and Justinian gave them this puzzle. He said, take this dream of weightlessness and make it out of stone, make it stand. That was the key. It meant that for the first time, theory came first. The whole design, every arch, even the mortar mix, it all started with geometry. It started on paper with calculations. They were building a prayer, and their tools were compasses and equations. That vision of a floating dome created a physical problem. How do you put a perfect circle on top of a perfect square? Builders had wrestled with that for centuries. They used these angular supports, squinches. They worked, but they felt like a compromise. The space beneath the dome felt fractured, interrupted. The square base and the round dome were always arguing. Isidore and Anthemius wanted no argument. They wanted a single, breathless volume of space. Their solution was elegant, almost magical. They invented, or maybe perfected, the pendentive. Look up inside Hagia Sophia at the bottom of the Great Dome. You see these four great curved triangles. They look like sails billowing out. Each one is a pendentive. They're the secret translators. They take the immense weight of the circular dome and translate it smoothly down onto the four massive piers at the corners of the square. Without a single harsh angle, it's a geometric miracle. The square walls curve inward, becoming these soaring triangular forms, which then become the perfect ring to hold the dome. There is no seam, no transition. It's all one continuous surface, one flowing idea from the floor to the heavens. That's why, when you stand inside, you don't see engineering. You see space itself, unbroken and immense. That was the first great secret. The pendentive didn't just support a dome. It dissolved the very problem it was solving. And it gave every architect who came after a new language for grace. That continuous space, that unbroken interior, created an even bigger challenge. The dome itself now had to feel weightless. Not just in theory, but in actual feeling. And the architects did it with a masterstroke. They cut 40 windows right into the base of the dome itself. 40 slender arches of light, so when you're inside and you look up, you don't see where the dome meets the wall. You see a brilliant, glowing ring. A circle of pure light, and it visually cuts the dome off from everything below it. This massive stone hemisphere weighing thousands of tons, it appears to just float. Suspended on this ring of sunlight, it's an illusion, of course, a beautiful, intentional deception. The dome is firmly supported, but your mind is tricked. It sees a miracle, a celestial bubble hovering in the air. That was a deliberate choice to prioritize spiritual experience over rigid structural logic. Because from a purely engineering standpoint, cutting 40 holes into the base of your main load-bearing dome is incredibly risky. You're weakening the very structure that holds everything up. It's like taking a crucial support beam and carving delicate patterns right into it. The builders had to calculate the precise size and spacing of those windows. To a degree that seems impossible without modern tools. They understood compressive forces so intimately. They knew exactly how much stone they could remove and where to keep the structure intact while creating that breathtaking visual break. And the light pouring through those windows, it does more than just illuminate. It dematerializes the boundary. It turns solid stone into an apparition. Light and faith. For a visitor in the 6th century, this wasn't just a building technique. It was a theological statement, written in geometry and sunlight. The heavens weren't far away, held up by thick, clumsy walls. They were right here, resting on a ring of divine radiance and that willingness to walk the line. Between structural daring and transcendent beauty, that is the second secret. It's the understanding that true awe sometimes requires you to hide the very thing that makes the wonder possible. The dome's weight, all that stone, wants to push the walls out, to collapse the whole thing. Centuries later, with Gothic cathedrals, the solution is right there on the outside. Flying buttresses, those stone ribs, they show you the force and they show you the answer. But Hagia Sophia's architects, they hid the answer. That's the third secret. A hidden skeleton, inside the skin of the building. From the ground, the exterior looks clean. A majestic silhouette, a dome resting on what seems like a solid block. No visible supports, no obvious struggle. It looks effortless, but that's the illusion. Wrapped around that central block, concealed, are massive external buttresses. Thick walls of brick and stone leaning in, shouldering the dome's thrust. And inside, the galleries and aisles, they're not just walkways. They're a complex internal web. Walls and arches, a hidden reinforcement grid, channeling the forces down to the earth in a specific path. Modern engineers have scanned it with lasers. Built digital models. What they found is a masterclass in empirical engineering. These builders didn't have the mathematics. They couldn't calculate stress vectors. They understood through trial, through observation, through an intuitive feel for how stone behaves. They built a support system so perfectly integrated that it disappears. The building doesn't look like it's fighting to stand up. It just stands, and that poses a question. We often celebrate structural honesty, showing the beams, the bolts. But here, the structural truth is veiled. The mystery is part of the message. The architects asked, what if the miracle feels more miraculous when you can't see the strings? What if awe is amplified by concealing the effort, not showing it? That balance between the brute necessity of physics and the delicate pursuit of wonder. It's a calculation we're still learning to make. The skin was the real magic, the fabric of the walls, the dome itself. They didn't build it like other monuments. Not with heavy limestone blocks. They used something lighter, a secret recipe, millions of thin, lightweight bricks, and between them a special mortar. It wasn't just glue, it was an active part of the structure. Historians and scientists have analyzed it. The mortar likely had volcanic ash, maybe from Santorini. When you mix that ash with lime and water, a reaction happens. It creates a material that hardens slowly, gains strength over decades, centuries, and as it cures, it stays slightly flexible. Not a rigid cement, more like a dense, resilient putty, an early form of concrete, but concrete with a memory. That choice had two effects. First, it made the whole building lighter. The dead weight on the piers and buttresses was reduced. That allowed for taller, more daring proportions. Second, and more important, that flexibility gave it a kind of life. It could sway, absorb the energy of an earthquake, let the whole building shudder and settle without shattering. For 1500 years, the ground has shaken. Other buildings from that time are gone, but Hagia Sophia settled. It shifted, the mortar flexed, the bricks slid microscopically in that flexible bed, redistributing the stress. So instead of one catastrophic crack, you see a web of tiny hairline fractures. The building breathed with the earth. This ancient composite material, found through trial and observation, prefigures our modern engineered composites. Today we design concrete with polymers and fibers for flexibility and tensile strength. We're just catching up to a discovery made in the 6th century. So the question isn't just about reviving an old recipe, it's about the philosophy. They didn't seek permanent, rigid perfection. They built for graceful adaptation. They partnered with time, with the inevitable movement of the earth. In our pursuit of stronger, more rigid materials, have we forgotten, to endure, a structure must know how to bend. That flexible, breathing structure, it was shaped by something invisible, the hand of mathematics. That's the 5th secret, proportional harmony. Every dimension, every space, it's all in a precise mathematical key. The architects, they had this belief: beauty wasn't a matter of taste, it was a law, a universal truth you could express in numbers. Geometry was the language God used to write creation. So to build a house for the divine, you had to speak it fluently. The dome's diameter is 107 Byzantine feet exactly. And its height from the floor to the crown is exactly half of that diameter again. That creates a perfect ratio. The whole central space is a square with the dome rising above it. And then the side aisles, the galleries, they're proportionally smaller. It becomes this rhythmic, nested series of spaces. Even the columns are placed according to these harmonic intervals. But this wasn't just for decoration. This mathematical precision was the bedrock of its stability. A perfectly proportioned building distributes weight evenly. The forces flow through it in a balanced way, predictable. There are no awkward stresses, no weak points from a clumsy dimension. The harmony you feel inside, that's not an accident. It's the direct result. Every line, every curve obeys a single set of governing rules. Today, we use computers. We run simulations to find the strongest shape for efficiency. But here, the strongest shape and the most beautiful shape were the same thing. The mathematics gave them both, the structural logic and the spiritual resonance. The building is a physical equation for awe, and it challenges our modern separation. We have engineers for strength, architects for beauty. Isidore and Anthemius wouldn't have understood that division. For them, the calculation that prevented the dome from collapsing was the very same calculation that made the soul lift upward. So it leaves you wondering. In our pursuit of pure efficiency, have we lost the code for true harmony, the kind that builds not just for the body but for the spirit? The mathematics gave it a perfect harmonic balance. But the real world shakes, it trembles. For 1500 years, the ground under Hagia Sophia has done exactly that. This building is in one of the most active earthquake zones on Earth. Its survival isn't luck, it's a conversation, a dialogue between stone and tremor. That's the 6th secret, an ancient strategy for living with the Earth's restlessness. They didn't try to fight the earthquake with rigid strength. They designed for something more intelligent, ductility. That's a modern engineering term. It means the ability to bend, to deform without suddenly breaking, to absorb a shock and then settle back. Hagia Sophia is a masterclass in this, built long before the word existed. There's the flexible mortar, the lightweight bricks. Together they create a shock-absorbing system. The whole structure has a gentle give, but the builders went further. They placed thin sheets of lead between some of the massive stone blocks. Lead is soft, malleable. During a tremor, the stones could slide just a tiny bit on that soft metal cushion. It was a planned slippage, a release valve for pent-up energy. So instead of building up catastrophic stress that would crack a cornerstone, the building could shudder, shift, and then settle. It dances slightly with a quake, and then the shape, the Great Dome, isn't alone. It's flanked by two half-domes and those by smaller ones, a cascading series of arches and vaults. This isn't just for beauty, it creates what engineers call redundant load paths. Think of it like a web. If one strand in a spider's web breaks, the others take up the tension. The whole web holds. In an earthquake, if one arch is damaged, the forces of the dome instantly find another route down. The structure has built-in backups. A silent resilience. Modern engineers studying this today are finding lessons. We now design skyscrapers with base isolators, massive bearings that let a building rock on its foundation during a quake. We use special steel frames designed to bend. The goal is the same: controlled flexibility. Hagia Sophia tells us that to endure the force of nature, you must have a plan to yield. Not to surrender, but to sway, to move with the chaos and then find your center again. It's a philosophy written in stone and lead, a lesson from the past that is modern. How do you build something to last forever? You don't build it to be unmovable, you build it to be unbreakable, and sometimes those are two very different things. Hagia Sophia had to speak, it had to sing. You step inside into that huge space and it's not silent. The air feels like it's waiting for sound. That's the seventh secret. An architecture built for the ear, engineered to turn human voices into something sacred. The goal wasn't just volume, it was to make the sound holy. To let chant swell and hang there, wrapping around people like prayer made physical. They did it by shaping the space, that great dome overhead. It's not just a roof. It's a giant sound reflector, a whispering bowl turned inward. A voice from the floor would rise, hit that curve, and fall back down as a slow wave. But if it was just one smooth surface, the sound would be a mess. A blur of echo, so they added complexity. All that marble on the walls, the mosaics, the hard plaster, that wasn't just decoration. It was a diffusion system. It broke up the sound waves, scattered them, so the sound didn't come back in one slap. It returned as a cloud, a rich, enveloping resonance that gave it a long reverberation. A note could last 10-12 seconds, blending into the next note and the next, creating those dense harmonies of Byzantine chant. The sound didn't just come from the singers. It came from the building joined in. There are stories of specific spots, whispering galleries, where a word spoken softly on one wall could be heard clearly far away. They understood how sound moved. They knew how to bend acoustics for a spiritual purpose. Today, architects design concert halls. They use supercomputers. They model reflection and diffusion. They build complex panels and baffles. And what they're trying to achieve is what Hagia Sophia has: a controlled, lush reverberation that turns performance into an experience. But here, this ancient church did it through an empirical feel for material and volume. They built for all the senses together, the visual awe of the dome, the cool touch of marble, the swell of chant in the air. It was all one design. It challenges a modern idea that structural engineering, aesthetics, and acoustics are separate things to balance. In Hagia Sophia, they're the same language. The curve that holds up the dome is the curve that perfects the sound. So you have to wonder, in our drive for efficiency, what have we silenced? Do we make buildings that look striking but sound dead? Spaces that look impressive but feel hollow? The ancient builders show us something. A truly great space doesn't just house an event. It becomes the instrument for it. Light has weight. In Hagia Sophia, it's a load-bearing element. That's the eighth secret. Light isn't just for seeing. It's a tool for shaping space, for shaping how you perceive it. It was part of the structural plan from the beginning. We mentioned the 40 windows around the base of the dome. But there are hundreds more, openings in the semi-domes, in the walls, up in the galleries. This wasn't random. It was a calculated perforation. They pierced the entire stone skin. And every window had two jobs. First, to physically lighten the mass. You remove stone where you don't absolutely need it. That reduces the dead weight. The weight the piers have to carry, but second, and more important, it dematerializes what's left. A solid wall becomes a screen. A thick pier becomes a form defined by shadow and highlight. The building sheds its heaviness. It turns into a lattice of light and stone. The architects understood something. Light can define a boundary. As clearly as a wall can, it can carve out a volume of space, make it feel larger or make it feel more intimate. Inside, the light is never static, it moves. All day, beams of sunlight travel across marble surfaces. They'll illuminate a column capital 1 hour, a mosaic the next. This dynamic play directs your attention. It tells a story with the sun. It makes the architecture feel alive, like it's changing, breathing. The space feels infinite because the boundaries are always shifting. Light becomes the primary material. Now contrast that with a lot of modern design. We often treat lighting as secondary, something you wire in after the walls are up. We rely on switches, on fixtures, but here natural light was the foundational system. The shape of the building was designed to harvest it, to sculpt it, to use it as the main source of awe. It makes you think differently. What if we designed buildings not just to be lit, but to be made of light? What if the sun's path was the first line on the blueprint? Hagia Sophia stands as a testament to that. It shows the most powerful structural element might not be stone or steel. It might be the immaterial beam of sunlight. The one that convinces you the stone is floating. The light was a blueprint, the schedule was a masterpiece, and the ninth secret, it's not in the stone. It's in the speed, the breathtaking speed of the assembly. The chronicles are precise: 5 years, 10 months, and 4 days. For a structure of that complexity, that scale, that timeline seems impossible. It would be an ambitious schedule even today. It hints at a logistical ballet, a staggering precision, a phasing strategy so advanced it still challenges modern project managers. Think of the scale: thousands of workers, marble shipped from islands across the empire, bricks fired by the millions, all converging on one site in Constantinople. Chaos would have been easy, but they orchestrated a symphony. The project likely advanced in concentric rings. While one team was still laying the deep foundations for the massive corner piers, another group could have been preparing stone for the ground-level arches. And as those piers rose, carpenters would have been building the intricate wooden centering, the temporary support frames for the great arches and the dome itself. Work overlapped, a carefully sequenced cascade. No team waited idle, no material delivery clogged the site. It was a continuous, flowing process, but this required more than a good foreman. It demanded real-time structural analysis. They were building innovations like the pendentives for the first time at this scale. The temporary wooden framework holding up an unfinished arch was under immense stress. A miscalculation in the sequence, removing a support too soon, could bring tons of stone down in a cascade of failure. They had no safety factors calculated by software. Their understanding lived in the minds of the master builders, passed down through hands-on experience. They read the structure as it grew, listening for cracks, watching for settlement, making adjustments on the fly. This integrated problem-solving where the designer, the engineer, and the construction foreman were essentially the same mind, it's something we've fragmented. In the modern age, we have architects, structural engineers, general contractors, often working in separate silos, their communication mediated by drawings and contracts. Here, the knowledge was unified and immediate. The challenge it poses is profound. We have cranes, computers, prefabricated components. We can build taller, faster in terms of raw assembly, but can we match the holistic efficiency, the seamless marriage of design intelligence and construction pragmatism? They built for the ages in less than 6 years. We build shopping malls in that time. It forces a question about our own priorities. Is our modern complexity, with all its specialized checks and balances, actually a barrier? A barrier to the kind of inspired, rapid execution that created timeless wonders. The speed of Hagia Sophia wasn't reckless haste. It was the product of a singular, unified vision. A vision where every person, from the quarryman to the bricklayer, understood they were part of building a miracle. That collective focus that might be the most powerful logistical tool of all. One we have yet to truly rediscover. That speed came from something deeper than just efficiency. The last secret is the biggest one. It's the way meaning and mechanics come together. In Hagia Sophia, every line, every curve, every proportion, it has two jobs. It's a structural need and it's a sacred message. They're the same thing. The building is a theological argument, but it's made of stone and light. The central dome isn't just a roof, it's the vault of heaven, and the square floor plan underneath, that's not just a stable base. It stands for the earth. Then you have those four great pendentives, the curved triangles that solve the geometric puzzle. They're the mediators. They've been called the four evangelists, or the four rivers of paradise, bridging the divine and the human. This wasn't decoration added on later. This symbolic geometry was the blueprint. It dictated the whole engineering challenge. The architects couldn't just say, well, a square base is hard, let's make it an octagon. Or a perfect hemisphere is unstable, let's flatten it a bit. The sacred form was non-negotiable. The spiritual meaning set the problem, and the engineering genius was in finding the solution that honored it completely. That's what created a holistic masterpiece. The strength of the building comes from its symbolic clarity, and the beauty comes from its structural truth. They're fused. Now, if you contrast that with a lot of modern design, we often separate these things. An architect has a vision for a form, then an engineer is brought in to figure out how to make it stand up. Sometimes there's a conflict. The beautiful shape has to be altered for safety, or the efficient structure ends up looking bland. The story of the building, its purpose, can feel like an afterthought. It's a plaque on the wall, not the language of the walls themselves. Hagia Sophia asks a quiet, monumental question. What are we building for? Is it just for shelter, for function, for a striking photo? Or can a building embody an idea so completely that its physical presence becomes a kind of wisdom? The challenge today isn't just to revive an old technique. It's to recapture that holistic view, to design so that the purpose of a library is felt in the quiet flow of its spaces, to build a school where the structure itself encourages curiosity and connection, to create a home where shelter feels like sanctuary because the geometry of the room tells it to. Hagia Sophia shows it's possible to weave story and structure into a single, unbreakable thread, where the reason you build something becomes the very thing that holds it up. The Hagia Sophia's great dome collapsed. This was in the year 558. Just over 20 years after the building was finished, an earthquake had hit, and the dome, the center of everything, it fractured. The central part fell straight down into the sanctuary. It was a complete catastrophe for the city, for the spirit of the place. Everything was shaken, but that failure, that collapse, it became the starting point for its real strength. The emperor brought in Isidore the Younger. He was the nephew of the first architect. His job was to rebuild, but first to understand. He looked at the ruins. He studied how it fell, and he saw the problem. The original dome was too shallow. It was beautiful, but it pushed outward too much. That horizontal force was overwhelming the supports. The balance was off, just slightly off. So his solution, he didn't just build it again, thicker. He changed the shape. He raised the dome higher, made it steeper. A little smaller in diameter. That new shape changed the physics. A steeper dome sends its weight down more, straight down, and pushes outward less. He was tuning the structure, adjusting the angles for stability, and he added more buttresses outside to handle the remaining thrust. That process, it's the real story. observation. Failure, analysis, then adaptation. The Hagia Sophia we see now, the one that stood for 1500 more years, that's not the first dome, it's the second one. The improved version, it came from the rubble of the first, and that shows you something. Resilience isn't about never falling, it's about learning how to rebuild. With more knowledge, the first vision was pure but fragile. The rebuilt one carried that vision forward, but now it was armored with what was learned. So failure here, it wasn't an ending, it wasn't hidden, it was the essential teacher. For this building, the collapse was the critical chapter, the one that made the rest of the story possible. It tells you something. Perfection isn't the first draft, endurance is written in the revisions. It's built on understanding what didn't hold. The second life of the domes, it depended on something you couldn't see. Something hidden under the ground, the real foundation of Hagia Sophia. It wasn't the marble, it was a mystery. The builders, they had an impossible starting point. Constantinople's soil was soft, waterlogged, unstable, like a sponge. You can't just dig a trench there, lay a cornerstone, the earth would swallow it. It would shift, it would tear the building apart, so the architects, they had to invent a different kind of root system. They probably built a raft, an immense, rigid platform. Stone and mortar, a grid that spread the whole weight of the cathedral over a vast area. A stone mat floating on that unstable ground. The building's colossal weight, it presses down everywhere at once. That evens out the pressure, it stops one corner from sinking faster than another. That disaster is called differential settlement, but a raft foundation on saturated ground, it isn't enough. Water is the enemy, it washes support away, it creates voids, it turns solid earth to mud. Recent surveys, they used ground-penetrating radar, non-invasive tools. They hint at the solution, they suggest a hidden network, a subterranean web, drains and channels built to manage the groundwater, to guide it away. To keep that foundation mat dry and stable. This was infrastructure thinking on a monumental scale. They weren't just building a church, they were re-engineering the very patch of earth it sat on. And here is the enduring enigma. We can't see most of this system. The building itself protects its secrets. To fully map it, you'd need invasive digging. That risks the structure it supports, so its true composition, its full genius, it remains partially unknown. It's a masterpiece we have to trust, but we can't fully examine. This challenges modern engineers profoundly. Today, we have incredible geotechnical data. We can model soil behavior with computers, yet we often design foundations for a building's lifespan. Maybe 150 years, Hagia Sophia's foundation was designed for eternity, on terrible ground, and it has succeeded for 1.5 millennia. Without catastrophic settlement, the question it poses, it's not about reviving an ancient technique. It's about reviving an ancient perspective. They built a dialogue with the site. Not a conquest over it, they listened to the problematic soil, and they answered with a wide, patient, intelligent embrace. In our race to build taller and faster on difficult land, do we invest enough in that silent, unseen conversation? The one happening below the surface, the part that truly holds everything up. The foundations held a mystery of process. How do you test a dome that's never been built? The answer is in a room with sawdust and light. Anthemius and Isidore built models, physical, three-dimensional scale models, carved from wood or shaped from plaster. These were working prototypes. They could hold the entire geometry in their hands, trace the curve of a pendentive with a finger, see, in tangible form, how the weight might flow from the dome down through the arches to the piers. A model makes the invisible visible. It turns an abstract equation into an object you can question. You can look at it from below, apply gentle pressure to a weak point and feel where it wants to buckle. This was their stress analysis, a quiet, tactile conversation between mind and material, but the models weren't enough. They were built on a deep, living library. The empirical knowledge of Roman engineering. For centuries, Roman builders had pushed the limits of the arch, the vault, the dome. They built the Pantheon. They built aqueducts and basilicas, and with each structure they observed, they saw which designs stood for generations and which ones cracked and fell. This wasn't written in a textbook. It was craft knowledge passed from master to apprentice on scaffolding, in stone yards, an intuition for how stone behaves under load. How much an arch can span before it needs a buttress. What mix of mortar allows for just the right amount of flex. Anthemius and Isidore were heirs to this vast, unrecorded database of success and failure. They didn't need to calculate the tensile strength of limestone from first principles. They knew it from the buildings standing all around them, so their design process was a triad. First, learning from precedent, studying what already worked. Second, hands-on experimentation, building models to test new, daring combinations of those principles. And third, informed intuition, the cultivated sense that lets a master look at a curve and know, in their bones, if it will hold. This loop of observation, modeling, and instinct is the direct ancestor of our modern computational analysis. Our software creates a virtual model and runs 1,000 simulations of stress. Their process created a physical model and ran the simulation through the most powerful processor available. The human mind, trained by experience, and this poses a quiet challenge. We can model a building's performance down to the last bolt, optimize for efficiency, for material use, for cost. It's a tremendous power, but in relying so completely on the digital simulation, are we risking the atrophy of that other kind of knowing, the tactile sense? The intuition born from physically handling materials, the understanding that comes not from a screen showing stress in red and blue, but from the feel of wood grain resisting pressure in a model. The most profound calculations for Hagia Sophia happened in a space between the eye, the hand, and the accumulated wisdom of centuries. It reminds us that technology is a tool, but not a replacement for the cultivated wisdom of the craftsman. The real breakthrough wasn't just in the shape they built. It was in the mind that could hold the whole impossible idea, test it with simple tools, and trust the answer it felt in the wood. Constantinople had this extreme climate, intense heat in the summer, then cold, damp winters, but inside Hagia Sophia it was different, a constant environment. And that was deliberate. That was the 10th secret. The building is a thermal battery. Every stone, every piece of marble, every brick in those thick walls has mass. And that mass has a function. During the day, the stone absorbs the heat. It soaks it in, so the interior stays cool because the heat is going into the walls themselves. Then at night, when it gets cold, that warmth starts to seep back out, radiating into the space. It creates a stable microclimate. The temperature swings get softened by the sheer inertia of all that masonry. The building breathes on a daily cycle. It inhales heat during the day and exhales it at night, but they also worked with the air. The window placement is a ventilation system. Lower windows on the cooler sides let dense, cool air flow in. That air would warm up from the people, from the candles, and as it warmed, it would rise. It would find its way out through the higher windows, up near the galleries and the dome. That creates a continuous, gentle draft, a passive airflow. It carried away dampness and smoke and the stale air from all the people. This did more than provide comfort. It was preservation. By minimizing temperature swings and managing humidity, it protected the gold mosaics. It kept the mortar from degrading. The building maintained its own interior. Now compare that to how we build now. We use massive systems. HVAC. We fight the climate with brute force. We seal buildings tight and then use huge amounts of energy to condition the air. Hagia Sophia represents a partnership. It uses physics, a thermal mass, stack ventilation as its mechanical system. It makes the building do the work. This poses a challenge to modern sustainable design. Today we add insulation, high-tech glass, solar panels. Those are good tools. But Hagia Sophia asks a more basic question. Before we add technology, have we used the innate intelligence of the materials and the form? Have we designed the building to be the primary climate battery? With climate change and high energy costs, this isn't just history. It's a blueprint, a reminder that sustainability might not be about more complexity. Sometimes it's about the simple power of mass and shade and the natural movement of air. That stable climate inside came from its mass, and that mass was part of something bigger, a living system. The real genius for its stability is how everything's connected. It doesn't have one backbone. It has a nervous system, a web of support woven so deep that no single piece carries the load alone. You look at the silhouette. The great central dome isn't an isolated bubble. It pushes out east and west into two massive half-domes, and each of those pushes out again into smaller quarter domes. It's a cascade, a hierarchy of arches and vaults, each one supporting the one before it, and being supported by the ones after. This is the architecture of a family. Not a monarch, the central dome's immense weight is shared. It transfers down through the four main piers, sure, but a huge part of its outward thrust gets channeled laterally along the curves of the half-domes, down through their supporting walls and out into the structure around it. That creates something, multiple parallel paths for gravity to reach the Earth. Engineers call that path redundancy. It means if one route is compromised, the load finds another. Instinctively, instantly, if a crack developed in one of the main arches, the forces would just divert. They'd flow through the adjacent vaults, through the thick gallery walls, through the hidden buttresses. The building would groan and settle, but it wouldn't catastrophically collapse. Its strength is communal. It's a lesson in stone for modern engineering, especially for earthquake zones, for extreme events. Today, when we design a skyscraper or a bridge for seismic areas, we build in redundancy. We create frames where if one beam fails, others pick up the slack. We design connections that allow for movement, for redistribution. We plan for the unexpected by making sure there's no single point of failure. Hagia Sophia shows us this isn't a new idea. It's an ancient, intuitive wisdom. Those builders understood that to endure for ages, a structure has to be a community of supports. It has to have a built-in conversation where every part talks to the others, sharing the weight of existence. That challenges a simpler approach to strength, a brute force approach. You could build a dome with piers 10 meters thick, and it would be strong, but it would also be clumsy. Dark and oppressive, the goal here was a different kind of strength, an intelligent, resilient strength that allowed for lightness and grace, a strength that came not from monolithic solidity, but from sophisticated collaboration. So the next time you see a modern building designed to withstand a once-in-a-century storm or a major tremor, remember, you're seeing the same principle that's kept this ancient dome aloft for 1,500 years. The principle that true resilience is never a solo performance. It is always a chorus. That resilient chorus of stone, it echoed far beyond its own walls. The engineering language invented for Hagia Sophia became a vocabulary for the ages. Those technical innovations didn't stay locked in Constantinople. They traveled, they were studied, adapted, reinterpreted across empires and centuries. The most immediate students were the builders of the Byzantine world. Churches from Greece to Russia adopted the core model, a central dome on pendentives, creating that unified, upward soaring space. It became the archetype for Orthodox worship, a physical theology replicated in stone from Kiev to Thessaloniki. The grammar of the structure, once a daring experiment, became a tradition. Then, in 1453, the city fell. The Ottoman Sultan Mehmed II stood inside the great church and was awestruck. He didn't destroy it, he converted it, and he challenged his own architects to learn from it. The greatest of them, Sinan, spent years studying its proportions, its hidden buttresses, its play of light. He saw it not as a finished masterpiece, but as a teacher. His own masterworks, the Suleymaniye Mosque and the Selimiye, are direct conversations with Hagia Sophia. Their attempts to refine its balance, to achieve even greater harmony and openness. Sinan sought to surpass his teacher, but to do so, he first had to listen to it deeply. The lineage is clear: the cascading domes, the flood of light from countless windows, the serene interior volumes of Ottoman classical architecture. These are the ideas of Hagia Sophia, translated into a new aesthetic language. The influence even leaped across cultures to ignite the Renaissance. In 15th century Florence, Filippo Brunelleschi was facing his own impossible dome for the Cathedral of Santa Maria del Fiore. He studied Roman ruins, yes, but scholars have long noted the conceptual debt. His double-shell dome, a revolutionary technique to lighten the structure, his use of a herringbone brick pattern for stability. These are solutions born from the same kind of radical, practical problem-solving that defined the earlier building. It wasn't a direct copy. Hagia Sophia represented a pinnacle of dome engineering that expanded the very imagination of what was possible. It proved a dome could be both a spiritual symbol and a structural triumph on a colossal scale. Brunelleschi was building in that expanded world. This is the profound legacy. A single building's technical breakthroughs seeded entire architectural traditions. It challenges the modern view of a structure as an isolated icon, a standalone statement. Hagia Sophia was never just an object. It was a living chapter in a continuous, evolving dialogue. A dialogue about how to enclose space with grace, how to make stone seem light, how to align structure with spirit. Every architect who studied it, from Sinan to the builders of modern Capitol domes, became part of that conversation. So the question for today's architects isn't just how to build something new. It's about listening to that long dialogue. What are we adding to it? Are we creating isolated monologues, or are we contributing verses to an epic poem written in light and stone? The true measure of a building's greatness may not be in its moment of completion, but in the centuries of inspiration that quietly flow from its walls. The dialogue with this ancient building continues. It's just in a new language now, light and data. Hagia Sophia is a living laboratory. Its stones are being read by tools the builders could never have imagined. Teams of engineers and archaeologists use three-dimensional laser scanners. They send millions of laser points across every surface, from the highest dome down to the deepest foundation wall. It creates a point cloud, a digital twin of the entire structure, accurate to within a millimeter, a perfect frozen moment in the building's long life. A map of every single crack, every subtle deformation where the building has settled, every variation in the mortar and brick. This isn't just a picture. It's a forensic record. They combine this with ground-penetrating radar, sending pulses down through the floors to sketch the unseen world beneath, the hidden buttresses. The drainage channels, the mysterious raft foundation, all of it begins to appear on a screen. Then comes the most powerful part, finite element analysis. It's a computer simulation technique. Engineers take that detailed digital model and feed it into software. The software divides the building into millions of tiny virtual elements. A three-dimensional mesh, then they can apply forces to it. They can simulate a magnitude 7.5 earthquake, identical to ones that have struck Istanbul in the past. They can watch in accelerated time how the stress flows through the pendentives, how the hidden buttresses engage, how the flexible mortar allows for microscopic movement. They can identify the precise points of greatest strain, the ones that have likely developed those hairline cracks over the centuries. What they are finding is a profound confirmation. The simulations often show the building's behavior under stress is nearly optimal. The load paths are efficient. The the redundancies work exactly as you would hope. The original intuitive design is validated by equations, but the scans also reveal something else, the story of care. They show the subtle, intelligent repairs made over 1,500 years. A patch of brickwork here, a reinforcing arch added there, a pier subtly thickened in the Ottoman period. The building is a palimpsest, a document written and rewritten by generations of stewards. Modern analysis lets us see each layer of that handwriting. It shows us the building's survival isn't just about a perfect first design. It's about a continuous, quiet conversation of maintenance and adaptation. Each repair was a response, a learning, a way of saying we see this weakness and we will gently correct it. This creates a unique challenge for modern science. A humbling one. We are using our most advanced technology not to design the future, but to fully comprehend the wisdom of the past. We are building digital models to understand an empirical masterpiece. The goal is to listen, to decode the silent language of stress and settlement the building has been speaking for millennia, and in doing so, we might finally begin to grasp the full depth of the conversation. The one that began with a compass on parchment under an emperor's impossible dream. The digital model shows the cracks, but it misses the gasp, that first breath when someone walks inside. That was the real calculation. The architects weren't just working with gravity and load, they were working with the human spirit. Every choice had a deeper goal. To shape a psychological experience, to build awe, the plan is simple. You come in through a low, shadowy narthex, a tight, intimate space, then you go through the doors. And the floor just drops, the space shoots upward. Your eye has no option. It gets pulled along the rising curves of the pendentives, straight up into the dome. That visual trip from human scale to the ceiling happens in a second. It starts a deep, primal reaction. A feeling of smallness, sure, but also a feeling of elevation. Of being linked to something much larger. The architecture doesn't just hold a ritual, it becomes the ritual. Looking up is the first prayer, then comes the disorientation. Where does the building stop? The smooth blend of dome and pendentive removes the hard corner. The 40 windows at the base of the dome melt its edge into a ring of light. Light floods in from everywhere, not from clear windows but from the walls themselves. The solid limits of the room seem to vanish. You're not in a box looking at a ceiling. You're standing inside a piece of infinity. This wasn't an accident. It was a planned removal of visual limits to create a sense of endless divine presence. To make the finite feel eternal, modern neuroscience has a language for this now. We study neuroarchitecture, how spaces change our brain waves, our stress, our sense of well-being. We know tall vertical spaces can create awe, which quiets the default mode network, the brain part focused on the self. We understand how soft light reduces strain and can bring calm. We have data that shows spaces without clear edges can encourage a more open state of mind. Hagia Sophia is a 1,500-year-old clinical trial for all of it. It's a masterclass in using scale, light, and shape not just to shelter the body, but to purposely change consciousness. And this creates the most subtle challenge for design today. We're brilliant at engineering for function, for efficiency, for sustainability, for cost. We can make a building that works perfectly, but can we engineer a space that feels transcendent? That actively grows wonder or peace or deep thought. The ancient builders worked from an intuitive understanding that we're now proving with science. They knew the shape of a space was also the shape of an experience. So the question now isn't just what a building does, it's what a building makes us feel. And how intentionally do we design for that feeling? In our schools, could the architecture encourage curiosity and calm? In our hospitals, could the walls help with healing? In our homes, could the space support connection and rest? Hagia Sophia stands as a quiet, massive argument that the highest goal of engineering isn't to beat physics alone. It's to use physics in service of the human heart, to build not just structures but states of being. The real test of a design might not be in square meters. It might be in the quiet moments where it takes your breath away. That sense of awe, it comes from the questions that are still there. We've scanned everything, we've made models, but Hagia Sophia keeps its secrets. The arguments among historians and engineers, they're just as intense now as they ever were. That mortar, the one that seems miraculous, we still don't know the exact recipe. Was it only ash from Santorini, or were there other local ingredients, a special way of mixing it, maybe even a curing process tied to a certain season, something that's just been lost? We can take samples and analyze them, but we can't recreate the living craft that went into it. Then you look up at the ribs of the dome. They get thinner as they go up, which is a brilliant use of material. But how did they figure out that taper? Was it from a geometric rule they knew in advance? Or was it a refinement, something passed from one mason to the next over generations? We don't have their original plans, so the building itself is the only text we have to read. There's a major debate about a hidden kind of strength. The dome wants to push outward. To resist that force, did the builders understand the idea of a tension ring? A continuous band under tension, like the metal hoop around a barrel, holding everything together. Some scholars see hints, discolorations in the masonry, signs of corrosion. They think maybe iron chains were set inside the brickwork, running around the base of the dome like a hidden belt. Brunelleschi used that technique in Florence centuries later. But is the evidence in Hagia Sophia actually clear, or are we just seeing what we want to see? There's no smoking gun, no surviving chain, no clear description from the time, so we're inferring from the fact the building has miraculously stood. It's reverse engineering history. These mysteries that last, they do more than just puzzle us. They show the limits of what we can know. They remind us the past isn't a puzzle to be solved completely. It's a conversation that keeps going. Every generation has new tools, lasers, chemical analysis, computer models, and asks new questions of the same old stones. The building is at the center of this ongoing discussion, a silent participant that challenges every assumption. It makes engineers think like archaeologists, and archaeologists think like engineers. That collaborative search across centuries, that's part of its legacy too. The structure isn't a closed book, it's an open invitation to look closer, to question deeper, and to accept humbly that some genius from 1500 years ago might still be ahead of us. These mysteries point to something bigger about progress. If you look at Hagia Sophia next to the great domes we build today, engineering doesn't seem like a straight line. It's more like a tree branching out. There's Buckminster Fuller and his geodesic domes, or Felix Candela, those thin concrete shells, modern marvels. They cover spans that would have been unthinkable in the 6th century, but they use a completely different toolkit: steel cables, lightweight alloys, concrete that's precisely engineered. They work with tension, pulling forces to make things light and strong. The Byzantines didn't have any of that. Their world was compression, pushing. The weight of stone wanting to go down. Their genius was in mastering that one language. They used shape as their reinforcement. The curve of a pendentive, the rise of an arch, the taper of a rib, all of it was a way to make gravity work for them. To channel that force along a set path. That mastery of compressive form is why modern shell designers still study it. A thin concrete roof today, like at an airport, works on a similar idea. Curvature gives it stiffness, turns a fragile sheet into something strong. Hagia Sophia is the ancient, monumental proof that the principle works, so the contrast is deep. One path leads to the ultra-light geodesic dome, a web of tension. The other leads to this massive stone vessel working in compression. Both enclose vast space. Both are triumphs, but they come from different material realities. That challenges a simple idea of linear advancement. It suggests engineering genius isn't just about moving forward in time. It's about solving the puzzle with the pieces on the table, which leads to a thought experiment. If you took today's top structural engineers but gave them only 6th century materials, brick, mortar, stone, timber, and the empirical knowledge of the time, could they match it? Could they build a dome on that scale with that feeling of lightness that lasts 1,500 years of earthquakes? The answer isn't a clear yes. They'd have the physics, the math, the understanding of forces that Anthemius and Isidore only intuited. But would they have the craft knowledge, the feel for that mortar as it cures? The instinct for when a wooden frame is under too much stress, the ability to read the building as it rises, to listen to it, that knowledge wasn't in a book. It was in the hands and eyes of a tradition, so the comparison isn't about which is better. It's about recognizing different kinds of intelligence. One is the intelligence of analysis of new materials. The other is the intelligence of synthesis, of deep material familiarity. Hagia Sophia stands as a reminder. Monumental achievement can flower from profound constraint. And sometimes the most advanced solution isn't the one with the newest technology. It's the one that perfectly, poetically, solves the problem with what's already in the room. The tree of engineering has many branches, but it all grows from the same soil, the soil of care. For Hagia Sophia, the biggest question now isn't how it was built. It's how we keep it. Its continued existence is a delicate equation. It's a living building, a mosque, thousands of visitors every day. Each person brings in warmth, moisture from their breath, and that humidity is a silent threat to the ancient mortar, to the mosaics. So preservation becomes a science of air. Sensors monitor the atmosphere, tracking temperature, tracking moisture, trying to maintain the stable climate the building's own mass used to provide. The goal is balance, to allow for worship and for wonder without letting the act of admiration become a slow erosion. Every time a crack is assessed, a stone is cleaned, a new question comes up, an ethical one. Should a repair use the original materials, the exact volcanic ash mortar fired in a wood kiln? That honors historical authenticity, the building's true fabric, but modern materials are stronger. Epoxy resins, advanced grouts, more predictable. They might offer better protection. But would that stronger fix alter the building's soul? Its survival has always depended on a gentle flexibility. A modern, rigid repair in one section could create a hard point, a place where stress concentrates instead of flowing through. In trying to save it, we might make it more brittle, more vulnerable to the next tremor. So the choice is never just technical, it's philosophical. Do we preserve the artifact, or do we preserve the behavior, the physical object, or the intelligent dance with physics that has kept it standing? This dilemma echoes everywhere, in conservation labs at ancient sites worldwide, from Venice sinking into its lagoon to the pyramids facing modern pollution. Hagia Sophia forces these questions into the open on a monumental scale. It demands that engineers, architects, archaeologists, and historians sit at the same table. They have to speak each other's languages. The engineer's need for stability must listen to the historian's plea for authenticity. The architect's vision has to accommodate the conservator's meticulous hand. This collaboration is the new crucible, the place where different kinds of knowledge are fused, like stone and light were fused 1,500 years ago. The building's role has evolved. It began as a church, then a mosque, a museum, now a mosque again. But through all that, its most enduring function might be as a teacher. A teacher of resilience, of harmony, and now of humility. It teaches that preservation isn't about freezing a moment in time. It's about stewarding a living story. A story written in cracks and repairs, in light and prayer, in stone that remembers every touch. The goal isn't to make it look new. The goal is to ensure it can keep telling its ancient, whispering story for another 1,000 years. And in doing that, it holds up a mirror to our own time, asking what we value, what we are willing to learn, and what legacies we are truly capable of sustaining. Hagia Sophia never had just one identity. From the very beginning, it was a conversation. It started as the great Church of Christ, a monument to one faith's idea of heaven. Then, centuries later, the call to prayer sounded under that same dome. It became a mosque, the walls covered in the names of God and the prophets in Arabic script. Now it's both a museum and a place of worship, but through all of that, the building itself stayed the same. The engineering, the actual structure, didn't convert. The pendentives didn't become Muslim. The dome's physics were only loyal to gravity, and that shows you something. The architectural solution they found was so fundamental, so true to structure and space, that it went beyond its original context completely. The container was more adaptable than anything it was meant to hold. So it's more than a historical palimpsest, a building written over. It's a symbol of synthesis. Its architecture created a neutral vessel, an awe-inspiring space that could hold completely different meanings across time without breaking. The engineering was a universal language. A language of light and volume and stability that different cultures could each interpret as their own. It speaks a dialect of geometry that every eye understands. And that challenges a modern habit. We tend to build for a specific moment, a specific ideology. Our structures announce their purpose, but what if the real achievement is to build something that quietly outlives its original intent? To create spaces with a universal grace that future people can inhabit and reinterpret. Hagia Sophia asks that question not with words, but by just standing there. It shows that a dialogue between East and West, ancient and modern, isn't just about decoration. It can be woven into the fabric of the building, into the way the weight goes to the ground and the light fills the interior. That structural honesty, that spatial generosity, becomes a form of hospitality, an open hand to the future. So the lesson for architects now isn't to copy a Byzantine dome. It's to aim for that kind of foundational generosity, to ask if a design has a core logic and beauty so clear that it could one day mean something wonderful to people we'll never meet. Can we build for a legacy of reinterpretation, to make not just a statement for our time, but a gift to time itself? That's the silent dialogue this building keeps hosting. Between the hands that built it and all the hands still to come that will just stand inside it and wonder. That universal language of architecture, from that transcendent vision, it still has lessons. The real gift of Hagia Sophia isn't a blueprint to copy. It's a mindset, a way to think again, and it starts with a radical kind of collaboration. The mathematician and the physicist, they weren't brought in later. They were the architects from the very beginning. Their theoretical knowledge, it wasn't just applied to a design, it was the seed, the starting point. That fusion of abstract thought and practical craft, that's the first thing. Today, we have specialists for everything: structural engineers, acoustic consultants, lighting designers, sustainability experts, but often they work in parallel. Their solutions get layered on top of each other. Sometimes they even conflict. What Hagia Sophia argues for is a deeper integration, right from the start. What if the team designing a new library included a poet to help shape the feeling of the space? Or a psychologist to understand how the architecture might foster calm? The goal is to make the collaboration seamless, like the pendentive, where you can't see where one discipline ends and another begins. And that leads directly to the second lesson, holistic design. In that ancient church, you can't separate the structure from the light from the acoustics. The acoustics from the meaning. They're a single, braided intention. The curve that makes the dome stable is the same curve that perfects the sound, that creates the illusion. Modern architecture often treats these as separate boxes to check. We add solar panels for sustainability, sound baffles for acoustics, public art for meaning. Hagia Sophia asks a more fundamental question. Could the building's very form be the solar panel, the sound baffle, the work of art? Could we design so that every line serves multiple purposes? Weaving function and feeling into one thing, that holistic thinking is what built resilience. And the third lesson is that endurance is a strategy, not an accident. Flexibility, redundancy, the capacity to adapt, these were designed in. The building was a partner to time, to the restless earth, for our era facing climate change that's urgently relevant. We have to build for adaptation, not just for the climate we have, but for the climates to come. Not just for the society we know, but for future generations who will reinterpret our spaces. That means designing buildings that can change use gracefully, creating infrastructure with multiple, redundant systems for when one fails, using materials that age with dignity. That can be repaired, not just replaced. Resilience isn't just a technical spec anymore. It's an ethical imperative, and this ancient structure is a masterclass in it. But beneath all these technical lessons is the deepest one. The fourth lesson, great engineering, the kind that lasts for millennia, is always driven by a transcendent vision. For Justinian and his architects, that vision was theological, a heaven on earth. Today, our visions might be different, a vision of true sustainability, of social equity, of healing connection in a fragmented world. The point isn't the specific creed, it's the existence of a higher purpose, a purpose that anchors every technical decision. When you're building to create or to foster community, to honor the planet, you make different choices. You invest in beauty that has function. You prioritize longevity over cheap speed. You solve for the human spirit, not just the need for shelter. For architects and engineers today, wrestling with urbanization, resource scarcity, Hagia Sophia is a quiet beacon. It reminds us that our most powerful tools aren't just new materials or smarter software. They are wisdom, collaboration, and a courageous vision that looks centuries ahead. It challenges us to build not just smarter, but with soul, to create legacies so thoughtful, so deeply integrated that they'll stand in 1500 years. Not as ruins, but as living teachers, still whispering. The dome is still floating. Its lessons are still there. We went from a burning city to a vision of heaven. Through mathematics turned to stone and a conversation with earthquakes that's gone on for 1500 years. This isn't just a story about the past. Hagia Sophia is a textbook, a living one. Its pages are cracked mortar and filtered light, the silent language of pendentives, the hidden strength of a foundation raft. Every chapter challenges something we assume now, the geometry that solved the circle on a square, the flexible materials that dance with seismic waves. They challenge the idea that progress is a straight line forward. What we find here is a peak of holistic understanding, a fusion of bold vision, empirical science, and profound meaning. Our age of specialization has trouble with that fusion. The monument whispers something. The greatest architectural triumphs aren't just engineering feats. They're conversations between the mind and the material, between a culture's highest ideals and the stubborn laws of physics. They happen when structure and spirit are seen as the same thing. So we look to our own future, cities that have to adapt to a changing climate, buildings that need to foster community and well-being. This ancient church offers a compass. A quiet one, a powerful one. It inspires us to look for solutions that aren't just clever and efficient, but also generous and resilient, to build with a vision that looks centuries ahead. To create spaces that don't just shelter the body, but elevate the human experience. The challenge isn't to copy a Byzantine dome. It's to recapture the integrative genius that conceived it. To build legacies again, legacies that will stand not as silent ruins, but as active teachers for generations we will never meet.